So, all this semester, all the material that we've learned, the last third of AB Calc, we started with talking about how do we find an area under a curve. So take a curve, and the question is, how do I find the area underneath that curve? Maybe I can make this a little shallower. From 2 points, from A to B. Glad to see the bells are working. Well, we said, don't know how to do it. However, we could break it down and kind of approximate it. And we use Riemann sums to approximate area under a curve. And what we did is we broke these down into rectangles. And we would find the area of the rectangle, sum up a bunch of rectangles together, give me a decent approximation of the area under the curve. First Riemann sum we talked about was a left Riemann sum. And what we did is we just summed all of our widths times what we call the left height. So let's go ahead and give this a table here. So let's give it x and f of x. And let's say when x is, we might as well start at 0. 0, we can say this is 2. 1, this is 4. 2, this is 7. 3, this is 10. 4, this is 15. Yeah, that's perfect. So we could say from 0 to 4. Well, if I were to draw these rectangles with these left heights, I would split this into all the different intervals. So from 0 to 1, from 1 to 2, to 2 to 3, and from 3 to 4. And I would take the height of, which is determined by my function, on the left of the interval. So my first rectangle would start right here. My second rectangle would start right there with that height. My third rectangle would be right here. And my last rectangle would be right there, using the heights on the left of the interval. So if I wanted to do a shortcut, I could do, the non-shortcut way would just be like a width of 1 times a height of 2, a width of 1 times a height of 4, a width of 1 times a height of 7. Instead, you could factor out the width and then just take the sum of your left heights, and that would be it. Okay? Then we said, well, we could do the same thing, but with heights on the right of the intervals. An example here, I would use these heights on the right to determine the shape of my rectangle. And in this case, you could do a shortcut by doing your consistent width times the sum of your right heights of each interval. We had a trapezoid, which would give us a better approximation. And that's just the sum of your 1/2 base 1 plus base 2 times height. And that's the formula for the area of a trapezoid. What ended up happening is you'd kind of connect these two left and right heights, and you'd pop a triangle on top of your left Riemann sum to give you a better approximation. Now, the shortcut, if the width is consistent, ends up just being 1/2 times your consistent width times your first height plus your last height plus double all of your middle heights. If you remember that. So in this situation, the width is 1 consistently. The first number, which would be my base 1, which would be 2. The last number would be my last base, which is 15, plus double the middle bases, which is 4 plus 7 plus 10. Okay, and then we had a midpoint Riemann sum, which is just the sum of your width times your height from the middle of an interval. So what we would probably do in this situation is only do 2 intervals, and we'd use that height of 4 for the first interval from 0 to 2, and the second interval would be from 2 to 4, and we use this height in the middle, which would be 10. So you'd end up with just, see if I can show that quick. It's a little crowded here. You just end up with 2 rectangles, but through the middle height. You can kind of see that. So that would be 2 times 4 plus 2 times 10, or 2 times 4 plus 10. Now, it's important, these shortcuts that we kind of showed can only be used if your width is consistent. Shortcuts. If the widths of the intervals are consistent. Okay, if they are not, you might have to do a bunch of 1/2 base 1 plus base 2 times heights for a trapezoid. You know, you just have to really actually do the calculations. Or you have to do, you know, your first width times your height plus your second width times your height. You can't just factor out the consistent width. Riemann sums are approximations. Depending on how your function is acting, whether it's increasing or decreasing, a Riemann sum may be over or under. To check to see if they're over or under, it's always good to draw a picture. I'm not going to tell you like the rules for if the function's doing this Riemann sum will always be over, or this is going to be under. Say I draw this picture right here, and then I ask you, is a left Riemann sum over or under? What would you answer for that? It would be over, because you're using the heights on the left, and that would pop my rectangles above my function, giving me more area than I'm looking for. Okay, typically a left will be an over, a right will be an under, which means your actual area is somewhere in between. That is important to know because you'll be given maybe a question saying what would be a possible number for the exact area. You'll be able to calculate the left Riemann sum and the right, and that will give you your boundaries. And you're like, okay, the answer has to be somewhere in between. But sometimes if your function fluctuates from being increasing or decreasing, we don't know if a left Riemann sum or if a right Riemann sum is over or under. Great. Well, then we talked about doing an infinite amount of rectangles and summing them together. And we came up with a new notation that is used for that infinite sum of an infinite amount of skinny rectangles. And what does that look like, that notation? An integral, exactly, a skinny s from A to B. That is what we said, okay, we're going to use that notation for an infinite sum. But what that represents is just the area under a curve from A to B. The exact area. Okay? Well, then we used this notation without numbers. This is what we called a definite integral. And this is what we call an indefinite integral. This is equal to a number. It's an exact area. This stood for what? Take the antiderivative. The reason why we use the same notation for what essentially seems like two different things is the connection between areas under curves and antiderivatives, which is the first fundamental theorem of calculus, which we'll talk about in a second. Okay? So take an antiderivative. Your answer is going to look like some function plus a constant. Let's talk about some definite integral properties. And then we'll talk about some antiderivative rules. So the key rule is if you have the area from, say, 3 to 4 of f of x dx is equal to 15, that means the area from 4 to 3 of f of x dx is equal to what? What happens when I flip the numbers? It'd be negative. Good. And a common one used on the AP test is, say I know the integral from 1 to 3 of f of x dx. That's 2. I know the integral from 3 to 4 of f of x dx is negative 5. I could find the integral from 1 to 4 of f of x dx. It would just be the sum of the areas from 1 to 3 and from 3 to 4, and in this situation it would be negative 3. Typically, they'll give you this one and this one on a question and ask you to find the first one. And you just know that, you know, from 1 to 4 is equal to 1 to 3 plus 3 to 4. So those are key integral properties. Another one is if we have a constant, maybe times a function. And this ends up being a antiderivative rule as well, but we can pull out that constant and then find the area under the function without the constant. All right, antiderivative rules. There's not many because antiderivatives are boatload harder than derivatives. And we really can't take the antiderivative of anything we want to. So we just have a couple. The first one is take the antiderivative of a constant with, say, with respect to x. What would that equal? Kx. plus some constant c. So that means if I just had dx, what's the antiderivative of just dx? X. Then really we talked about the power rule, the kind of simplest one. If I have x to the n, and I want to take the antiderivative. What I do is I add 1 to that exponent, and I multiply by the reciprocal of that number. So that means if I have, say, x to the 5th, and I want to take the antiderivative, add 1, multiply by the reciprocal. Kind of like the opposite of the way you do derivatives. Derivatives, you move the number down first, and then you subtract 1. Antiderivatives, add 1 first, then multiply by the reciprocal. There's simple trig function antiderivatives, like sine. Antiderivative of sine is actually not cosine, it's negative cosine. That's because the derivative of negative cosine is sine. Antiderivative of cosine is just positive sine. Some special ones. Antiderivative of 1 over x was what? Natural log absolute x. The absolute, since natural log is only defined for x is bigger than 0, the absolute kind of covers the left side of 1 over x. And then the antiderivative of v to the x was just e to the x. Well, learning this rule probably hurt us when asked to do this antiderivative. Because everybody thinks, okay, after learning this special rule, that the antiderivative of this is log absolute x squared. But that is wrong. Instead, we use the power rule, and what we have to do is rewrite this as x to the negative second, and then add 1, and then multiply by the reciprocal. Same thing occurs when we deal with e in the denominator. Everybody thinks, learning the natural log rule, that the antiderivative of this is natural log absolute e to the x. But that as well is wrong. Instead, you need to rewrite this as e to the negative x, and then we're actually going to use u substitution to find that the antiderivative is e, negative e to the negative x. So let's talk about u substitution. It was the one rule that helped us do a couple tricky antiderivatives. And a good example we can use is, say, the antiderivative of x squared times x cubed plus 4 quantity to the 5th power. Okay, let's remember we set u typically equal to the inside of a composition. We then take the derivative of both sides of that. However, we essentially take the derivative with respect to a different variable, and then we cancel like with respect to t. So I get du dt on both sides, or du dt on one side, dx dt on the other side. And then I multiply by that dt, the dt's go away. So what we say is that the derivative of this is du equals 3x squared dx. Okay, and we only do it with this notation when we're doing this u substitution. because it helps us pop up this dx. What I then do is I solve for dx. Then I substitute in u, and I substitute for dx. So this becomes x squared u to the fifth. Dx becomes 1 over 3x squared du. Now, if all is right in the world, if I have du here, I can only have u's in here. And in this situation, I do that because we have those x squareds that cancel. And now I have something that I can take the antiderivative of a lot easier. Just add 1 multiplied by the reciprocal, and then plug u back in and simplify. However,
wait, is that plus 6? Or is that
that should be plus c.
Yeah, that's it. I always do that.
However, there is something that we need to be careful about. Say I have the integral from 2 to 4 of f of 2x dx, and I'm told that's equal to 5. I might be asked to rewrite that in terms of u's. So I can say u is equal to 2x, du is equal to 2 dx, dx is equal to 1/2 du. I can substitute in my u. And I can substitute for dx. But what happens is these numbers must change if I change things to u's. This is an x, and this is an x. If I have u's and u's, these need to be u's. Well, the key is that connector. Setting u equal to 2x means if I have x's, multiply them by 2, I now have u's. And then I can factor out the 1/2 and multiply both sides by 2. And I say, okay, this is equivalent to f of u du being equal to 10. And if I talked about going back to this previous one, if I had numbers here like from 1 to 2, once I change this to u's, this needs to change into u's. So this would be from 5 to 12. And then if I wanted to evaluate this, I could either evaluate it with 5 and 12 using u's, but that's essentially the same as evaluating it from 1 to 2 if I plug x's back in. Why? Because if I plug in 12 in for u, I got 12 to the 6th. Here, if I plug in 2 for x, 2 to the 8th plus 4, or 2 to the 3rd plus 4 is 12. I get 12 to the 6th either way. Okay? But typically you will be asked a couple problems where they require you to change your boundaries. So please be wary of that when you use u substitution, that you must change your boundaries. All right, those are the integral properties. Now, the antiderivative properties. Now we talked about the connection. The connection is established from the fundamental theorem of calculus. That says, say I want to find the area under f prime. Essentially, I just need to find the change in f, which is the antiderivative of f prime, and that would give me the area. So what started out as meaning just area under the curve turns out also means the change in my antiderivative function. So we have two meanings to that notation, integral from A to B. Not just area, but also the change. And when I applied this, if I say we're looking for some f of b, I can manipulate this equation up here to solve for f of b. And I say, hey, if I want to find a future value, I can just take an initial value and then add the change in my function, which is represented by the integral from a to b of f prime. And we can use that to find future function values. So there's two ways now in which we can solve a situation like this. F prime of x is equal to, say, x squared plus 3. F of 1 is equal to 4. What's f of 3? One simple way is if we could do this, I could find the antiderivative of this, and I can essentially find c and find what f of 3 is. So I take the antiderivative, I get 1/3 x cubed plus 3x plus c. I was told that f of, let's say f of 0 is equal to 4 just to make this easier. F of 0 is equal to 4, that means c is equal to 4. Now I can use this function f of x is equal to 1/3 x cubed plus 3x plus 4 to find f of 3, just by plugging in. So that's one way that just makes sense. I can find the antiderivative function. However, if I had a situation where I have f prime equal to, say, log x times e to the x squared, and f of 0 is equal to 4, what's f of 3? I can't take the antiderivative of this. So I can't use this find c method. Instead, I apply the FTC and I say, all right, well, f of 3 is just equal to this initial value 4 plus the area from 0 to 3 under this f prime, which essentially stands for the change in f from 0 to 3. And you can plug that into your calculator and you'll get the same answer as if you could find the antiderivative. Okay, remember that? We did that back in the day. We also had different applications of these infinite sums. We found an average value of an infinite amount of numbers or of a function. And we turns out the average is related to the area. You just multiply 1 over b minus a to the area from a to b under f of x, and what you get is the average f of x. That's very important. If you're asked to find the average velocity, even though velocity is the antiderivative of acceleration, you're not going to use acceleration or you're not going to use position. If you're trying to find the average velocity, you plug your velocity function into your integral, and that will give you your average velocity. Then let's talk about distance and displacement. Before we talk about that, we can talk about the relationships. We know the derivative of position is velocity. The derivative of velocity is acceleration. That means the antiderivative of acceleration is velocity plus a constant c. The antiderivative of velocity is position. And then antiderivative of position would just give you the antiderivative of position. Or you could use it to find average value, average position. Okay? Now, if I wanted to find displacement, I can take the area under my velocity. That's taking all of my velocities that are positive and negative, multiplying them by those infinitely skinny times. And, of course, we can say that's the area under your velocity curve, or your change in the antiderivative, and that stands for displacement, if we're talking about the change in position. Now, when I want distance, I want to account for going to the right, going to the left, having positive, having negative velocities, including those into distance. So going to the left is increasing my distance. So when I want to take my positive velocities, keep them positive, take my negative velocities, make them positive, I use an absolute value of my velocity, and that gives me distance. Okay, we should remember that. Then we introduced this accumulation function, and we said some g of x, some function, is equal to the area accumulated from a to x of some f of t dt. This probably looks foreign to you, but we did it like 2 chapters ago. So if I wanted to find, say, like, if g of x was equal to the area from 1 to x of, I don't know, some function, I could find, say, g of 1 by plugging in 1 for x. Keeping f of t dt the same, I know, and this was an integral property that we should have talked about, that the area from 1 to 1 is just what? 0. Okay? But what was really interesting, move this away. I think. Is that when I took the derivative of this with respect to x, I got that g prime of x was equal to, what did this turn out to be? I took the derivative of this. Just f using x's. So a quick example of g of x is equal to the integral from 3 to x of t squared sine t dt. G prime is just equal to x squared sine x. Without even a c, no c's, nothing. And it doesn't matter what this number is. So this is the derivative of this, and this is the derivative of this. That means this is the antiderivative of f. Which is why typically they didn't use G, they used capital F. So say I give you a question, what is the derivative of this? Or no, what if I say, what is the antiderivative of x cubed e to the x sine x? You'd be like, well, Mr. Messenger, that's impossible. I can't do that. Well, you actually could answer this in a little tricky way by just putting this in the accumulation function and just use t's. This is considered the antiderivative of that.
Why would you have to use the t to make the antiderivative? Can't you?
Because it's got to be an accumulation. You got to go from a to a variable with respect to another variable in the function. Now, the accumulation function, there's a lot of questions that relate to, when does G have relative maxes and mins? When does G have inflection points? And we just have to kind of associate the correct things. If I took the derivative again, and if I wanted to analyze G double prime, it's essentially analyzing F prime. I'll be asked different questions about G, and you're going to be given stuff about F, and you have to use it to tell you about G. We'll go over a couple of those. Those are common. But we also need to go over what happens if I have a function here. And let's say, I don't know, t squared or something there. If I take the derivative of this, we need to remember that, yes, you are going to, with respect to x, yes, you are going to plug in the function where t is. But then you need to take the derivative of f prime and put it at the end. It's kind of an application of the chain rule. This is dt, this is dx. So let's just show you an example of that so we don't forget. If I said from negative pi to 3x squared of the e to the t sine t dt, and you wanted to take the derivative with respect to x of that, that would be equal to plugging in that function where t is times the derivative of the function. And you will be given a question just like that on the test, where typically people remember to plug in, but they forget to multiply by the derivative. And these are problems that should be super, super simple to do if you just remember this rule. May 8th, Wednesday. Okay, so then we had a lesson, a unit on differential equations. Simple one like dy dx is equal to x squared y. We must remember a differential equation, the solution, if I ask to solve this, well, the solution is an equation. Solution is the equation whose derivative is x squared y. First thing we must remember with any differential equation, and make sure we write this down, is separate your variables first. If you don't remember to separate your variables, you're going to get 0 points on a differential equation free response problem. So example here, I would divide by y, multiply by dx. Second step is to find your antiderivatives. You would get log absolute y plus a c, but what we can do is move that c over here and make it a different c. Typically we solve for y, so I take e to the power of both sides. Make sure when you're taking e to the power of this side, you put that all in parentheses, giving you absolute y is equal to this. Well, now my c is up here in an exponent. I can use a property of exponents to bring this c down and make it e to the c times, I'm going to show you all these steps, and you guys can remember whether or not you skip it or not. So you can bring that e to the c down, and say it's a product of e to the c times e to the 1/3 x cubed. But e to the c is just a positive number. It'll always be positive. We can assign it some value, positive or negative, by getting rid of this absolute and just saying this is some other constant that now is positive or negative. And this is what would be your solution. Okay, and there's all sorts of differential equations. They can come in lots of different ways, but the process is the same always. Separate your variables first, take the antiderivative, go from there. And of course, area and volume, we just went over that unit. So I'm going to just have you guys remind yourselves about that. Okay, a bunch of pi r squareds, it's a bunch of dy's, dx's, between two curves, top minus the bottom, or right minus left, depending on if you're doing dx or dy. If you have questions, you can ask me, but these should all be in the back of your notes. Okay? How much time?